Recording in progress.
Christopher, sorry, I don't see the cursor.
No. Move the mouse to the right.
Okay.
Yeah.
Okay, welcome back. It's a pleasure to chair this last session of this workshop. Our first speaker in this afternoon session is Hang Tran from the University of Medicine, and he's talking about level set forced mean curvature flow with a Neumann boundary condition.
Thank you.
Please.
First of all, I would like to thank the organizers for having me virtually here, and of course, I would love to be there in person, but hopefully, again, like other speakers have said, it's going to happen soon. So I will talk about a sort of weak formulations of solutions for mean curvature flow with forcings together with Neumann boundary conditions. So those are interesting sort of phenomenon that being coupled together, and it make the problem interesting. And this is a joint work with Jiung Zhang, who is my PhD student and who is also here virtually. Do-Hin Kun, who is my postdoc, and then with Professor Hiroyoshi Mitake at University of Tokyo. So let me start right away. I want to focus only on this concrete problem today. So I will just tell you right away the geometric meaning of the equation that we care about. So we are given a domain here. So we are not in the whole Rn. We are given a domain omega here. And what we require for the Neumann boundary condition is a homogeneous Neumann boundary condition. So we require the right angle condition. This is sort of like in Professor Giga's talk. There was also the right angle conditions. Whenever we have a this is just a 2D picture, or whenever we have a surface, if it intersect with the boundary, is intersect in the perpendicular way, and then inside of the domain omega, I have that the surface is being controlled by a forced mean curvature. So the velocity, the normal velocity, is v equals to kappa plus c, and actually c here equals to c of x. So basically, the front or the manifold is being moved not just by mean curvature, but also by a given velocity c of x, which is we consider the problem in homogeneous media. That means that the velocity is different at different places, and the question is that how do we describe the motions of sort of this surface as time goes. And again, this is the right angle conditions. Our motivations comes from various sources. For example, it comes from front propagations, or like in flame propagations, like in forest fire and stuff like that. In such a case, if we are looking at the media, at locations in which that we have trees, for example, then the velocity is faster, and at location in which that we don't have tree, for example, in the location as of the velocity is slower. Also, that we are motivated from crystal growth, in which that in different locations in the media, the growth speed is different, and that's why we want to sort of consider the velocity that is a variable in x. What is sort of interesting in this problem, of course, is that we have not just the mean curvature, which is really the key point here, but also the variable velocity together with the right angle conditions, right? So the question is that as time goes, are we sure that this front is going to be kept the same, or once we move further and further down the road, maybe we're gonna encounter some topological changes, like the talk yesterday, right? But because we have the boundary condition comes into play, so there's gonna be a balance or the competition between all those things, and it's sort of actually not clear in the first topological change what happens, right? Either we have the singularity formed because of the mean curvature, but also we can have the singularity forms because of the boundary condition. So that's sort of our motivation. As I said from the beginning, we are concerned with the level set formulation. So it's a weak formulations. Here we only have one phase. We have a comparison principle. So the level set formulation is, I think that it was mentioned already. We look into, so we look into geometry, which is just the level set of all the x, so that uxt equal to 0, right? And then we look into the evolutions of this level set, but because it can form singularity, so it's easier than to look into the PD for u, right? Which is sort of the equation that encoded into u, and this is clearly a sort of a forced mean curvature flow equation. There are two terms here. The first term, du times diversion of du over du, is the mean curvature, and then the second term is the first order term, cx times du, which is the normal velocity in the normal directions at each of the point x. And the right angle conditions becomes a homogeneous Neumann boundary conditions. This one is the homogeneous Neumann boundary conditions, and then we input in the initial data u0x, and then for compatibility, this is not needed, but just to make sure that we started with the right setting. So for compatibility, we assume that the initial data is C2 with 0 Neumann boundary condition. And the Neumann boundary condition here for this irregular problem, for this Cauchy problem, is understood in the viscosity sense. So it's in the weak sense. And let me tell you why. Because as I said, as the surface evolves in time, there can be singularity, and actually it's not clear, and it hasn't been systematically studied even up to this moment, according to my understanding, is that if we have the singularity formed on the boundary, then what happens sort of precisely there, in a final way, then it hasn't been studied. And let me give you a very simple example in this aspect. Because we can see that the domain is not convex, right? So let's say I take this is the origin, I take like a slice out. So maybe this is sort of my domain here. Okay. So U is my domain here. Of course, I mean, my domain has to be C2. So therefore I have to smoothen up a little bit this point at the origin. So maybe this is like that. And then I'm now just gonna look at my front at the beginning. It's just gonna be part of the circle with center at the origin. Pardon my drawing, but this is sort of my front, and clearly that at the beginning is the right angle condition satisfied. And let's assume the C is constant or even 0, doesn't matter. And we look at the evolution of this front. So either C is constant or C is smaller than the mean curvature term dominates. So therefore it's shrinking, right? So I mean, when it starts shrinking, everything is still nice. It's shrink down to smaller circle or smaller sphere, and it keeps shrinking to smaller sphere. And the right angle condition is always satisfied. However, as we get closer and closer to the origin, we started maybe encounter singularities because again, at the origin, we have to actually, because we have to make the domain smooth, so we have to take out sort of this smaller part. So when it gets closer to to the origin, then maybe there are going to be topological changes here in the surface, right? Maybe it's going to be split into two or so, and therefore the Neumann boundary condition has to be understood in the weak sense, because we want to consider the equation past singularity for all time. Yep. So that's sort of why I think that is interesting. And again, I mean, please stop me if you have question or concern. What are our main goals here? Again, I mean, there are competitions between the mean curvature, the forcing, which is variable. So it could actually make things sort of not homogeneous. Like the picture I drew earlier, C was constant or zero. And then also the boundary of omega, we don't assume it to be convex, which is typically the case in the literature when dealing with the Neumann boundary condition. People typically assumed earlier that the omega is convex. So our goals are really going sort of past the well-posedness theory. We want to study, of course, I mean, regularity of the solutions. What we can hope for the best is always Lipschitz regularity in the theory of viscosity solutions. So we want to study when do we have Lipschitz regularity in space and time. And what is really important is that we want to have Lipschitz regularity globally for all time. So of course we're going to need to put some condition on the forcing term C, so that we have Lipschitz regularity, and the condition on C gonna depend on the geometry of omega, right? Because there's curvature in omega in different locations on the boundary, and we are also concerned with the fact that we're gonna surely impose conditions on C, but the conditions can be too rough, right? Might not be, very optimal. So we really care about that. If we put conditions, are they sharp? Are they really optimal? And if we violate it a little bit, then do we lose a global Lipschitz regularity? And also that because we consider the weak formulation, we pass singularity, we can define solution for all time. And the question, motivated by crystal growth, was that we want to study lifetime behavior of the solution for all time as time goes to infinity. And not just that, we want to characterize the limiting behavior of the solution. I'll mention those more clearly later on. Those the stationary problem, the question about characterizations of solution looks pretty much like a certain sort of Alexander type theorem. Anyway, so those are our main goals. So let me tell you very briefly the literature. I'm probably missing a lot of references here, and forgive me if I forget some of them. Just give you a very brief list. So of course, as mentioned in various talks, if we consider the level set formulation is first started from the work in numerics by Osher and Setian, and then rigorously independently by Chen Gigagoto and Evans Brook for mean curvature flow. And later on, actually, the question about force mean curvature flow, if we are in the whole domain without any boundary conditions, then so after the three works here, Osher Setian, Chen Gigagoto, and Evans Brook, the paper that study homogenizations for force mean curvature flow in the whole Rn was Leon Suganidis. So because we are in inhomogeneous regime, so we want to study, as the scale goes to zero, what's the sort of limiting equations. And of course, after that, there are many papers on homogenizations and other directions in this aspect. For example, there are some papers by Caprelli and Mono, I'm not mentioning here, but it's really interesting. And for the Neumann boundary problem for level set mean curvature flow, then we are aware of some works, very, very interesting work by Giga Sato, Giga Onuma Sato, or Osuka. Some are without forcing, so only mean curvature, and some with constant forcing. And typically the case here is that the domain is assumed to be convex. And prior to that, if we only consider, not only, but if we really consider the graph mean curvature flow with Neumann boundary conditions, and in the 80s up to now, there are a lot of amazing works, for example, the work by Christian or Wan, or recently by Ma, Wang Wei, or Mizuno and Takaso. It's really interesting. And if we assume that the Neumann boundary condition is zero, for example, not zero, if we consider sort of capillary type boundary conditions, and still there are a lot of open questions. Here we only focus on the homogeneous Neumann boundary condition. And also we have motivations coming from crystal growth. In crystal growth, that, as I said earlier, we have sort of like the growth of crystal inside a inhomogeneous media, in which that we have sort of like the crystal is being grown by various sort of materials already sort of floating around. So that's level set mean curvature flow, but there's also the source term. We have that motivation coming from the work of Giga, Mitake, and myself, and others. And that's also one of the motivations for us to start studying this kind of problem. But again, I mean, today I'm only focusing on this very simple setting. Okay, so let me tell you right away some results we got, and then I will give you certain ideas. You know, what sort of interesting, what's new here, and some of them are also, I mean, the strategies are pretty standard. So not all of them are, you know, like interesting, but dealing with the boundary conditions and sort of understanding deeply the interplay between them is really our motivation. So this is the first result about a global Lifshitz estimate that we want to again obtain when, under which condition on the forcing term, coupled with the boundary conditions that we have, the solution is globally Lifshitz. So, you know, I'll describe them, but basically we're going to put some condition on the forcing term, which is this thing, this sort of condition on C. So if we have this condition on C, then the solution is globally Lifshitz in both space and time. So the constant M and L are only depending on forcing term in initial data, but doesn't depend on space and time. So this condition in the literature of you know, level set mean curvature flow or Hamilton-Jacobi equation, sometimes we call this one is sort of coercive condition. Sort of, I mean, not exactly, but sort of coercivity of C. What we want is that 1 over NCX square grow a bit faster than the length of the gradient. So the delta is a small number. And on the right hand side, we have max of 0, sure. But the second term is concerning with the geometry of the domain on the boundary. So let me describe them to you. So we have this sort of boundary omega that we don't assume it to be convex, so therefore we need to take into account the curvature, right? So basically the second terms here is exactly that. So we want to let C naught to be exactly the maximum of minus lambda, for lambda is the eigenvalue of dn on the boundary. So what's sort of the maximum of minus the eigenvalues for all points on the boundary. And the second term, K naught, is the minimum of D. For D is the diameter of open inscribed balls in omega. For example, if I take this point, I'm going to try to draw the sort of biggest ball that is inscribed in omega, touching the boundary at X, and this is going to be the diameter here gonna be exactly dx, and I'm gonna take k naught to be mean of all such diameters. So clearly that if the domain is nice, then we wouldn't encounter very small inscribed balls, right? But if the domain is very bad, for example, if the domain is sort of gonna be having this next sort of smaller and smaller, stuff like that. If this is our domain, then k naught can be very small. Nevertheless, it's always a positive constant. So if we impose the coercivity condition on C, that is 1 over n C squares growing faster than its gradient at n faster than the term we put on the right hand side is a term concerning the geometry of omega, then we have the solution is globally licious. Okay, so there's one remark I want to make. Sorry, my space of writing here is a bit tight, but one remark I want to make is that in case we consider omega to be convex, then when omega is convex, then clearly that C naught is non-positive, right? Because we have take max of minus lambda. So when omega is convex, then the right hand side of the conditions 0.2 is going to be 0. So there's going to be that what it means is that if we take omega to be convex, then we don't have to worry about the geometry coming into play. But if omega is not, then we have to be careful. So I'm gonna tell you briefly the proof of this theorem, and then we're gonna see why the geometry comes into play, and then later on, let me say it right away that we're gonna give examples that you can see that this condition we impose here, this condition 0.2 here is actually optimal. What I mean by that is that if we violate this condition even just a little bit, then our solution is not going to be globally Lipschitz anymore. So that's sort of the key point here. And also, by the way, once we have Lipschitz conditions, then we can run the comparison principle. For example, in the previous books that I mentioned, or in Giga's book, once we have a priori estimate that one of the solution is Lipschitz, then we have well-posedness, we have uniqueness of solution. That's not hard to do. Okay. And then the second result, I'm not going to mention this, but you can wonder, I mean, why do we have to impose the condition on C, right? So in fact, as a matter of fact, we don't have to impose condition on C if we only want to have local estimates. So what I mean by that is that if we only assume, sometimes it's okay. Yeah. If we only assume that C is C1 up to the boundary without imposing the coercivity conditions, again, the earlier coercivity conditions involved with this sort of thing, minus delta greater than equals to the right-hand side. It can be 0 or something involves the geometry. If we don't impose this kind of conditions, and in fact, we still have well-posedness, we still have the solution is still Lipschitz in time, but we're gonna only have that the solution is locally Lipschitz, in space. I mean, okay, I have to be careful what I'm saying here. What I mean is that it's still Lipschitz in space, but the Lipschitz constant Ct here really depends on T, and Ct might blow up as T goes to infinity. So we in this still have local Lipschitz estimate, but the forcing term is really funny. I mean, it can actually, as time goes, it can force things to go wrong, and then the Lipschitz constant is blowing up. In certain example, it might be interesting here. I mean, I don't know, but it might be interesting to study more about the rate of blowing up in such a case, like the rate of blowing up of the gradient in X. For example, if we don't impose any condition, then what's sort of this rate of blowing up as t goes to infinity? What the rate? I don't know. It might be interesting. We haven't got that very precisely. We only prove that in some examples it's blow up. Okay. So let me tell you very roughly the strategy of the proof, and you can see that this is rather classical when we consider the like level set framework. Is typically the case that the earlier formulations is we have du times diversion of du over du, and this is sort of like singular, or it can be bad if du is equal to 0, right? So it's a very natural way it started, coming back, or all the ways to approximations of singular problems or degenerate problems that we often try to sort of make it nicer. And here we are just doing it in a classical way. We try to approximate the early equations by something that is nicer. So for each of the parameter epsilon greater than 0, we're going to consider this approximated problem. When we add epsilon here, epsilon square plus du square, then it makes the denominator always positive, right? So, because that's just a technical thing, but also this is sort of essentially the graph mean curvature framework as well. Anyhow, by adding epsilon square, we avoid the problems of having du equals to 0. And then if we can prove that du is bounded, then we are in exactly the framework where the equation is uniformly parabolic. Right? So if we can prove that du epsilon is bounded from above, then we are in the uniform parabolic region. And then we try to then pass to the limit, let epsilon goes to 0, and it's always the case for us that we want to get certain uniform estimates a priori, independent of epsilon, so that we can pass the limit. Yeah, so this is that. It's not surprising. It's still already from the earlier works by Evans Berkeley. And again, what is really interesting here is that we need to understand what happens on the boundary. It's not hard to get the time derivative that u epsilon t is bounded. This is not hard. Maybe let me go back to the equation. Let me just say it in words. Here to prove it, we use the fact that the PDE is independent of time. In other words, if u epsilon xt is a solution, then you can shift it like to epsilon t plus h is also a solution for h fixed. So we can shift it around, right? Because the equation is independent of time. In a sense, we are using Noether principle, right? If we can shift it around, then we can just compare the two solutions. And we get that once we can compare them, then we get by comparison principle, we can get the u epsilon t is bounded. That's not hard. Then what remains is that we need to prove that du epsilon is bounded by constant c. How do we do that? We use the classical Bernstein method, and then because there are a lot of top experts in the audience. Let me just tell you briefly. I mean, what's the point of the Bernstein method here is that there are tedious computations, but basically we look at the PDE for u epsilon, right? So we have f u epsilon equals to 0, certain nonlinear equations, and if we differentiate that, if we linearize that, and then so u epsilon solves the equations that f u epsilon equals to 0, then we would have that if we differentiate in space or time, then it's going to solve the linearized equation. Okay, so it solves the linearized equation, and then what we do using the classical Bernstein method here is just that we take a convex function acting on u epsilon xk. So if we take any phi that is mapping from R to R that is convex, then Bernstein method tells us that phi u epsilon xk, if we act phi on u epsilon xk, then it's gonna be solving that linearized equation, but we're gonna have an additional term, a good terms coming out, and that's exactly the Bernstein method. And for example, if I take du here, it's gonna be du is solving the linearized equation, right? So I take w epsilon is gonna be this convex function acting on u epsilon, or you can take other functions, so in this approach, we take w epsilon is going to be just square root of epsilon square plus du epsilon square. Actually, you can do the same thing. You can take phi epsilon to be du epsilon square. It's also work. It's just any sort of reasonable convex function acting on du epsilon. So if we do so, by some tedious computation, we end up with essentially a kind of linearized equation. So W is going to solve this linearized equation again. And one thing that there is a good term here that coming out from this convex trick. So it's Dij, Bkl, Uki, Ulj. So this is a good terms coming out. And because of this good term, we can just use Cauchy-Schwarz inequality to get a good terms coming out, which is you can see that it's 1 over n ut minus cx times w squared. So you see that from here, that's the reason why we have the terms 1 over n cx squared. It's really coming from this good term. So by using that, then we can get a priori gradient estimate. So far, all of this is classical. So when we do the maximum principle, right, we want to bound W epsilon, which is square root of epsilon square plus du epsilon square by maximum principle. Then the interior case is easy. If the maximum occurs inside omega, then we just use exactly the classical maximum principle. And then by using the previous equation, again, you can ignore all the tedious terms. I know that this is already the end of the conference. So if we ignore the tedious terms, what we see is that we're going to end up with this thing. So dc times w square is going to be greater than 1 over n times this square. And this exactly allows us to come up with the condition that is 1 over n cx square minus dc minus delta greater than 0. That's exactly that. So inside, we don't feel the curvature or anything. Inside, if we impose this condition, then we exactly see that we have the gradient bound. Okay. Now we're gonna feel the curvature if we are on the boundary. So the second case that of course is we cannot get rid of that, right? So we have to consider the case that x naught is on the boundary. So what happens if the maximum occurs on the boundary? Then first, typically the case that we handle this situation is that if the maximum occurs on the boundary, we're gonna try to actually push it in, right? So we're gonna try to sort of draw a maximal an inscribed wall here. We're going to try to make the maximizers comes in by introducing certain multiplier essentially. And this is where our approach is new, and this is where we can sort of feel a bit the real sort of behavior of the boundary. And it's now that we use the fact that we have the homogeneous Neumann boundary conditions. Again, if it's not homogeneous, then for example, capillary type boundary condition, then it's harder. There's still a lot of open questions there. But if it's homogeneous, then we can just differentiate it along the surface, right? This is the computation on the surface, because we always have that on the surface around here, du times n equals to 0. So the computation on the surface gonna allow us to come up with d squared u times n equals to minus dn times du. And recall that again, recall that w equals to root of epsilon square plus du epsilon square. So if we compute, right, because we are doing maximum principle for w, right? So we need to understand what's the normal derivative of w at that point. So just doing this computation, by just using chain rule, we have this, and we have this, and we notice that surely du is perpendicular to n. So du is perpendicular to n, which means that du is in the direction in the tangent plane or tangent surface, right? So we can apply these conditions here with the vector du coming into play. So we have d squared times du times n over w. By this relation is equals to this term. So minus du dot dn dot du. So it's dn and matrix acting on du, right? And this is where we use exactly that the conditions that we have to take into account the curvature, right, or the eigenvalues of dn. So if we denote by c naught is maximum of minus lambda for lambda and eigenvalues of dn, then this terms here is going to be less than equals to c naught times w. Okay, that's the best that we can do, because again, I mean, of course, we wouldn't know where the maximizer occurs, right? It can happen at any point on the boundary a priori. Therefore, to bound this, the best we can do is sort of just to take supremum of minus lambda, maximum minus lambda. So we have that. So at the end of the day, for W, we don't have the homogeneous Neumann boundary condition anymore. We have del W over del N is less than or equal to C naught times W. So a certain grow condition occurs here. And again, if we are in the case that we have the domain is convex, then the C naught is less than or equal to 0. So that can be ignored, which is good. But in general, C naught is we have to take into account C naught. Okay. So to take into account C naught, then here we're going to introduce a multiplier rho. So the goal of the multiplier rho is sort of like to push the max inside. Right. So again, maybe let me try to draw again the picture here. Oh, I have to keep track of time. I have to speed up. So this is a point x naught. We take this is exactly the inscribed ball with touching the boundary at x naught. We have to try to push the maximizer inside, and again recall that we have del w over del m is less than or equal to c naught times w. So this is sort of like by using normal sort of OD type techniques, right? So we try to let C equals to rho times omega some W, and rho is something we can design so that we push the maximum inside. And again, by just elementary calculation, we have this. del C over del N is equal to this, and then this is less than equal to this. So if we choose rho, so that you know rho equals to 0 at sorry 1 at that point, and always less than equals to 1 on the boundary, and rho at x0 satisfying these conditions exactly 0, so that it cancel things out, then we are able to you know push the maximum insides, because for the function c we have del c over del m is less than 0, right? What it means is that, you know, in this is x naught, this is the one. If the normal derivative is less than equal to 0, then that means that the maximum has to stay inside here, and that's the goal of the multiplier rho. And you know, this is one of the multiplier that we came up with. There can be many other different kinds of multiplier, but this is great for our purpose. It's just a downward parabola. Okay, so with this multiplier coming into the gap, we can push the maximum inside, and then we can apply the maximum principle. It's a little bit tedious, but the flow is clear. With the help of this multiplier, eventually we can come up with these calculations that's sort of exactly serving our purpose, that the left hand side is exactly you know 1 over nc x squared, and the right hand side is now, you know, because the all these things occurs because of the occurrence of the multiplier rho, and they corresponding exactly to C naught, which is the maximum minus the eigenvalue, and then k here is exactly the inscribed ball, the radius of the inscribed ball, because you can see that in the previous picture I have to put the inscribed ball here, so the radius comes into play. So we have that that box in which we have exactly the condition we need to impose. So therefore, if we impose that condition, then we have a global Lipschitz estimate. Okay. Of course, you can say that, you know, that condition we put it, it's pretty much forceful, right? You know, like then how do we make sure that that's optimal? So I'll come to that. Okay. Right. So now, you know, so we given that condition 0.2, that is 1 over ncx squared minus dcx minus delta is greater than or equal to max of 0, and that conditions on the boundary. Then we have that the solution is globally Lipschitz, and once it's globally Lipschitz, then we care about large time behavior. Then we can prove this is this result is pretty standard. We can prove that as time goes to infinity, uxt gonna converge to v, stationary solutions, and v solves this stationary equation. So as I said from the beginning, what is actually really open and interesting is sort of to characterize all solutions to this equation. Characterize all solutions to this. And of course, you know, even in the case that that C is constant, because if C is constant, you can see that this is analogous to sort of the Alexandrov theorem, in the sense that, you know, like what's going to be all possible solutions that have sort of constant curvature, right? But then the point here is that we also have the sort of like the Neumann boundary condition on the boundary. So do we have like those, the level sets are parts of the critical spheres or what? Anyway, so the characterization is still open. So the proof of this of this large time behavior is quite standard. So I just mentioned it very quickly. It's just by using the Lyapunov function. This already occurs in the 80s in the study of mean curvature flow. and up to now it has been used various number of times. And when we study the lifetime behavior, then for this typical problem, this Lyapunov function is useful. With exactly the Neumann boundary condition. In general, it might not be useful, but if we use this Lyapunov function and by some careful computations, not hard, we end up with this changes that the d over dt of the term on the left hand side is always less than equals to this one on the right. And because u epsilon t is bounded, so by integrating it in time, we get that the integration for any upper time t of u epsilon t square is always bounded. And it's clear that if you let t goes to infinity, sort of like heuristically in this picture, this integral is everything, right? But it's still bounded. What it means is that, roughly speaking, u epsilon t should go to 0 as t goes to infinity, right? And that gives us certain stability. And then we can use the, like stability results in viscosity solutions to obtain the desired result. So I just sketch it here. We can essentially use stability results. We can first, let a sequence of tkj goes to infinity, and we would have ux of t plus tkj converging to v. And then we just need to show that vt equals to 0. So it's the solutions is independent of time in the limit, because we have this limit is constant for all t. So it has to be independent of time, and then we just need to show that the solution is independent of the choices of the sequences. So that's not a big issue. We can prove that. Okay. So now let me move on. One case that I want to mention that we can understand deeply the behavior of the limiting solution is that we consider the radially symmetric case. Omega is a ball, yeah. And everything is radially symmetric. C is just depending on the radius r, and U is also radially symmetric. In this case, then of course, also for mean curvature, right? When we have just a sphere, then we understand clearly its behavior. And similarly here, if we consider the problem in the radially symmetric setting, then this is just the curvature term, right? N minus 1 over r, exactly the curvature. And this is the forcing term. And then we have Neumann boundary conditions and initial data. What is interesting here is that, of course, this is not, there's still an interplay between mean curvature and the forcing term, but this becomes a concave Hamilton-Jacobi equation. Concave Hamilton-Jacobi equation, and now we can use the tool in Hamilton-Jacobi equation to study its behavior. As my time is almost over, so let me go quickly. So it's a concave Hamilton-Jacobi equations, and we can look into the Lagrangian framework. We take what's the Lagrangian corresponding to this Hamiltonian. We have, this is that, and then we can use optimal control formula to find this formula for the solution phi of RT to be exactly this. Again, this is u of xt equals to phi of xt, which is phi of RT. So we can look into the solution in this aspect. And again, by using Lagrangian framework, we can see that phi is nothing but supremum of just u0. So I mean, the schematic picture, this is the point R, this is t. So at this point RT, we can try to use all possible parts to go back. Again, I'm using now the optimal control framework, and among all the possible parts that are admissible, we look at what's the maximum supremum value of u0, and this is going to give us the value of the function. And because this is the Neumann boundary problem, actually is quite complicated. We here use the squirrel code problem And this was studied by Hitoshi Ishii earlier for the Neumann boundary problem. So what we can prove is that we can characterize fully the limiting behavior of the solution. And what is really interesting here is that, this is sort of typically a sort of related to dynamics, but is you can see that this also comes rather naturally, even if we don't mention WKM or dynamics into the gap. We can see that what we see here is this is from 0 to R. We need to distinguish I, which is the regions in which that we have CR equals to n minus 1 over R. This is the regions in which they have the balance between the mean curvature and the forcing term, so they balance them out. So this is cancellations. So let's say that I have A is the unions of, let's say, A1, B1, A2, B2. So in those regions that I have A3, B3, in those regions I'm underlying here are the regions that I have CR equals to n minus 1 over R. So those are where the forcing and the mean curvature balance each other. And then there are other regions here that from 0 to A1, B1 to A2, B2 to A3 are the other regions in which I have either is in A plus or A minus. So CR is less than n minus 1 over R or greater than n minus 1 over R. So those are the regions in which either the mean curvature flow is stronger or weaker. Okay. Then we can prove that in the limit, the solution, so I have phi of RT converging to phi infinity of R. So in the limit, we can prove that if we are in these regions, that the mean curvature flow is balanced with the forcing term, then the solution is supremum of U naught R for R greater than equals to R naught. If we are in the regions that A plus, that CR is greater than n minus 1 over R, then we have a supremum of U naught R, but R starting from BI. So starting from BI. And then similarly, if we are in the other region, then we have R starting from AI plus 1. Okay. So you might ask, why do we care about this? I mean, of course, it's always the case that understanding the limiting profile is important to us, large time behavior. And the simplest thing we can always do is always looking into the radially symmetric setting, because the other setting we haven't understood it yet. But even so, this radially symmetric setting already gives us something phenomenon. You can see now that, so this is example. So we consider CR to be this form. So it's going from 0 to A to B to R. So in the between from A to B, we have CR equals to n minus 1 over R. Okay. From 0 to I, we have CR is less than n minus 1 over R, and here we have CR is greater than n minus 1 over R. So if we assume that we start with this profile of U naught, the initial data, then in the limit, the solutions, you see that, in these regions from 0 to I, this should be I, then this one becomes supremum of all possible values here. So it's going to be this one. This regime, because decreasing, is being kept, and this one is decreasing, but when we take supremum of all possible value for OB, it's becoming this. So you see fattening phenomenon here, right? Even though we start with the level sets that are not fattening, but in the limit, we see that, there are two regions here that we have the level set are being fattened. So that's the first thing. The second thing that we want to say is that if we consider an initial data that is of this form, so I have this is Bj and Aj plus 1. If we consider the initial data to be 1 here and less than from 0 to 1 and 0 here, so this is U naught, then in the limit, interestingly, even though we start with everything nice, you know, and maybe all the level set, there's nothing fattening, but in the, I mean, nothing fattening here from bj to a j plus 1. But in the limit, what we can prove is that the solution going to converge to something discontinuous. So it's going to converge to 1 here and 0 here. So even though we start with everything nice, Lipschitz or so, but in the limit, the solution going to converge to something that is discontinuous. So there's jump of discontinuity, and this allows us to actually show that based on that earlier result, we can show that the condition we impose is optimal. Why is it optimal? So I mean, at this point, bj here, we can assume, so this is n minus 1 over r. We can assume that our C touches bj from below at this point. So this is C, the forcing term. If it touches bj from below at this point, then we have this condition C bj equal to this and C prime bj equal to this. And if we just compute it, we're going to have this computation. So earlier, we always have to require 1 over nc square minus c prime or dc minus some delta is greater than 0, right? But in this case, if we violate it just a little bit, so you see that in this computation, I have 1 over nc square minus c prime in 1D here is equal to this term, is less than 0, right? But if I let bj goes to infinity, this one is approaching 0. So it can be very, we are just violating it just a little bit by putting something just tiny and near 0, but still we have that in the limit, the solution is, the limit is discontinuous. That means that U is not globally Lipschitz. So this is really the key point that we find that it's amazing that what we put is optimal. Okay? So let me end my talk by maybe just giving you this picture. We have another example. This is based upon the examples constructed earlier by Giga Onuma Sato or Otsuka, that we can also, you know, similar to the picture I drew earlier, we can sort of construct a very classical examples that the domain is sort of like this is omega created by these two curves from above and below, which can be computed clearly. You know, we just know that we can compute it, and then we look at the evolutions of sort of parts of the circles here, and we can keep track with the evolutions clearly. And then we can also prove that in this case, we lose the Lipschitz regularity as time goes to infinity. So, you know, so it's those evolutions of parts of the circles. And this is the second example that shows that we don't have global Lipschitz estimate as time goes to infinity. Okay, I think I'm a bit over time, so let me stop here. Thanks a lot for your attention.
Yeah, thanks for this interesting talk. Are there questions? Let me ask a short question. So can you go to the page 6 where you stated the optimality condition?
Yes.
Or this I think you call it coercivity condition.
Yes.
Yeah. So what surprised me a little bit is the fact that this you say that this is optimal, but you would also expect such a bound to hold without an external field, right? So if C0, but so that means that would be excluded here, right? So if in a convex domain, your right hand side is 0.
Yes.
So then
so you know, in the convex domain, and I have the right hand side is 0 because I don't have the interplay of curvature on the boundary anymore. But still, uh, the condition says that 1 over nc square minus dc is greater than 0. Uh, so if c is not too nice, for example, if c changes sign, or if c is small, very small, then in fact something can go wrong. For example, there's a paper by Luis Cavalli and Regis Mono, where they study that they don't have the non-boundary conditions, but let's say that the right hand side is 0. So if this condition fails, then they can prove that you know, in the limit there's no homogenization. So in a similar way, that the setting is that we don't have Lipschitz estimate. Um,
Okay, and then I'm surprised, probably because I don't really understand this problem well, that there's no interaction, or it seems to be no interaction of your external force and the boundary condition. So, I mean, I would have expected that the situation is getting worse in situation where your force field is, for instance, tangential to the boundary, or at least I don't see this interaction.
now I understand your question better. Yeah, so so the condition we put is that, for example, like what you said, if c is 0 on the boundary, so let's say on the boundary, if my forcing term c is 0, then this condition is violated, right? Because I always need c to be a bit positive. This condition you see, like 1 over nc square, let's ignore dc. It has to be greater than delta. So if on the boundary, if my forcing term is 0, for example, then actually it's not good for me. I'm violating it. So actually that's a great question. Let's assume that cx is equals to constant c. Then the condition I would need to put at least is 1 over nc square is greater than delta. I need c to be either a bit negative or a bit positive. If C changes sign, then it doesn't work for me.
But I don't understand why a constant force field. Okay, it's because of the Neumann boundary conditions that the constant force field. I mean, if I have mean curvature flow and I have just a constant forcing, then it's just a spatial translation, right? So then I don't see why this improves the Lipschitz conditions.
No, I'm just saying that we have global Lipschitz estimate for all space and time. I'm not saying that it improves the conditions. So what you said is absolutely correct. In the case that we don't have the Neumann boundary conditions, then we can prove that for constant forcing we always have Lipschitz regularity.
Okay, but then let me go back to the second question. So why don't you see an interaction between the boundary condition and the forcing? If the in the sense that if the forcing is tangential to the boundary, I would assume that there's the regularity is getting worse, or is this picture wrong?
Maybe let me go back. There was a picture I drew. So so this is the first picture, right? You see that at this point, for example, like what you say, right? I mean, because it's
So maybe tangential is not good, but maybe the forcing is doing something ugly at the boundary. So pushing the level sets against the boundary, something like this.
Yes, and what I said also is that I don't think that there is a systematic study on topological changes on the boundary. So let's say that the first time we see topological changes is not um, because of the manifold, but because of the boundary. Then I haven't seen any systematic study on this aspect yet. So what we impose here, the condition we impose here is understood in the viscosity sense. So it's a weak sense. What imposed here on the boundary? It's really in the weak sense. We haven't understood like until what time that we have holes in the classical sense, and then at that time, what really happening on the boundary then.
Okay, thank you. Other questions or comments? I think this is not the case, so let's thank the speaker again.
Thank you very much.
And I think we're having now a coffee break until 3:30, and then we resume with Susanna Terracini.